As mentioned, I'm Kecheng Huang from the Chinese University of Hong Kong. I'm the final year PhD student. And today is my pleasure to be here at FAST, representing our work team to present our new work, HaSiS, a hardware-assisted single index store for hybrid transactional and analytical processing. This work, I think we will start from the HTAP, the hybrid transactional and analytical processing. HTAP, which is a well-known data processing architecture for simultaneous execution for both OLTP and OLAP, which is a very critical component in modern applications. And it affects many domains like finance, advertisement, and also the e-commerce. And as for the key criteria of the HTAP system, normally we focus on the performance of OLTP and OLAP. And as for the OLTP, which normally encounters the small random records updates or search operations, and as for the OLAP, it typically involves some kind of large-scale attribute or column scans. So basically, there are some conflict between such two workloads. As for another key criteria of the HTAP system, I think the real-time and data analytics is a very important metric for modern HTAP system because currently we want to, as soon as possible, to execute the newly ingested OLTP updates by the OLAP real-time query. In detail, as for this work, we focus on the well-known conflict of storage, of optimal storage format between the OLTP and OLAP inside the HTAP system. So basically, as for the OLTP system, it prefers the row-based storage format because it could mitigate the I/O amplification when they ingest the small-sized updates or search operations, and they can maintain better update efficiency. On the other hand, as for the OLTP system, basically they do not like the row-based format. They favor the column-based storage format for better I/O efficiency because, as mentioned, as for the OLAP request, they will normally involve the batch scan or batch load operations. So as for existing work, basically multi-index HTTP designs the mainstream of the existing HTTP system. They primarily follow a mixing design to mix the row-based index and the column-based index altogether to provide the HTTP service. And to achieve the real-time data analytics, they rely on the data synchronization, or to say the cross-index data cross-index domain data migration to achieve that. And in a more detailed way, as for the multi-index HTTP design, they can be categorized into the multi-index multi-store and the multi-index single-store design. And there are many representative work focusing on optimize such two approaches. So specifically, as for the first category, the multi-index multi-store design, basically they will separately maintain an OLTP engine with the row-based index and another OLAP engine with the column-based index, and separately provide the OLTP and OLAP service. And they rely on the cross-domain data migration to provide the real-time data analytics. But this design, it is very traditional and very typical. It faces several limitations. The first is the resource-consuming data moment. Because they maintain the data in the two engines, they need to periodically migrate, or to say merge the data from one from another. So it is very resource and time-consuming. And this consuming work also introduces another data freshness problem because the data cannot be immediately applied to the row store or the column store when you want to perform the OLAP real-time query. So as for this design, there are some pros and cons. And another category is about the multi-index single-store design. Basically, they will kind of, rather than separately maintain two engines, they will only preserve one single system, but build a row-based data tier atop of the primary column store that maintains the column data. And this design, it is kind of novel and also widely deployed in modern HTTP systems. But this design, they also face some limitations, like because now we maintain all the data in a single system, which means for either OLTP or OLAP query or request, you need to go through all the data. For example, for the OLAP query, you need to not only access the primary column store, but also you need to access the data in the data space that maintain data in a row-based format. And correspondingly, they will cause a kind of severe performance degradation within the larger than memory data set, because normally we will maintain the upper layer inside the memory. Well, as for our work, we identify the problem here is that data in the existing designs are separately managed in distinct index domains, and the cross-index data migration essentially introduces significant overhead. And the challenge here is that we want to simultaneously achieve the optimal OLTP performance and the OLAP performance, and meanwhile provide the instant data freshness for OLAP queries. And here in this work, the key here is rather than relying on the original distinct index design, we want to leverage the new story hardware to bring us some opportunity to rethink this problem. Basically in this work, we focus on the CSD with built-in transparent compression. So here it is a special computational storage drives with the data compression functionality. Okay, so the first feature of the CSD with transparent compression is that it has the low-cost compression. It can transparently provide the compression or decompression capability inside the SSD without affecting the normal routine and the critical path of the data service. And such an operation or deep operation engine is very efficient and with low latencies when they conduct the compression and decompression operation. And another key feature of the CSD with built-in transparent compression is that it could provide the virtualized logical storage space. And this could further enable the sparse data management, which is very important and brings us opportunity to rethink how do we design a new HTTP system to simultaneously achieve the goal we proposed originally. Well, based on the new CSD devices, we have several insights. The first one is that the CSD could decouple the random amplification from the page size. Originally, as for an OLTP system, basically they rely on small size page to maintain data because they want to mitigate the I/O amplification. If not, if you do not want to that small size page, you need to maintain a huge monolithic log to accumulate the updates to the pages. But the log here, we have a trade-off, like the log is too big, the recovery performance could be worse because we need to replay many log records during recovery. But if the log size is small, we could not sufficiently accumulate such updates. But here, after involving the CSD, this problem disappears. Like we could distribute the originally monolithic huge log for each pages to convert the originally monolithic log as the per page logs. This could mitigate the recovery overhead, but meanwhile provide the optimal performance for OLTP request. In other words, in our HTTP design, we will not rely on the small size to guarantee the optimal performance for OLTP. Well, another insight is that the CSD could mitigate the read amplification for OLAP queries. Originally, as for the typical OLAP design, they prefer to tightly assign the data into the data block, like the page, to save the storage space. But this layout could introduce the read amplification when they perform the column-oriented query. So in CSD here, the idea is kind of the same, like we could sparsely manage the column-based data column by column instead of tightly align them inside each 4 kilobytes data blocks. So here, the read amplification could be avoided. And the third one is that the multi-version record in the system that provide the concurrency capability. So here, because we have the CSD, originally the separately managed temporary data here could follow the same idea to be assigned with each page, such that we will not face the performance degradation and extra retrieval for OLAP, and also the garbage collection could be simpler than before. So based on such insights, we propose our HaSiS design, hardware-assisted single-index store. And here, there are three major components, like the hybrid buffer pool, the small global log, and the hybrid page format with per-page logs. Based on such component, we want to deliver the insight and the opportunities provided by the CSD and to achieve the goal. So firstly, as for the hybrid page layout, basically it follows our insight analysis. Like we want to use largely relaxed B-tree page to provide efficient service for OLTP and OLAP. And for the column-based page, we will sparsely align the column data into each data block instead of the original way we tightly align them into data blocks. And for the row-based data page, which is assigned for each column page as distribute the original monolithic log as per-page logs. And then we have the log and compression mechanism to efficiently ingest the OLTP updates into the main storage, and then we want to achieve such ingestion and meanwhile provide the OLAP request with optimal performance. So here we want to better utilize the high bandwidth of contemporary SSDs. So here we propose the major and minor compression to deepen the queue depth of the SSD devices to efficiently ingest such operations. And also we have the buffer pool to isolate the performance between the OLTP and OLAP, and we utilize a validation-based approach to achieve that. And more details for the hybrid buffer pool and also the details for other techniques could be found in the paper. Whereas for the evaluation, we have implement a fully functional prototype and also a benchmark tool. And our evaluation is built atop volume production ScaleFlux CSD devices. And as for the evaluation result, so basically we first compare with contemporary OLTP and OLAP performance to figure out our performance potential. So basically compared to the contemporary OLTP system, basically we have the comparable performance compared to MySQL and PostgreSQL, and we also implement a row store baseline, which is a B-tree based QL store. And as for the OLAP performance, basically the conclusion is the same. We could deliver the comparable performance compared to the Parquet and also a column store baseline. And then we compare with representative HTAP system, the TiDB. So basically, the conclusion is that we could deliver the more stable and instant data freshness for OLAP request. And meanwhile, our performance to both OLTP and OLAP is comparable to the TiDB. And finally, it's about the effects of optimization, like the storage usage of our design. So basically, because we have the transparent compression, we will not obviously occupy the extra physical storage space. So as for the conclusion, we propose the HaSiS, which is a CSD-enabled single-index design. And we want to address the long-standing trade-off between the data freshness and the performance in the HTTP system. And we conduct our evaluation on top of a commercially available CSD platform by leveraging its capability of sparse data management. Yeah, I think that's all. Thank you.